Welcome to the video demonstration of an implementation of the OSCORE profile phase framework. This video is brought to you by the University of Montenegro and the SPOTS team. You can find more details about the SPOTS project at spots.ac.me. The ACE framework under standardization in IETF specifies the use of OAuth2 three-party authorization protocol for constrained environments. The framework can be instantiated with different web transfer and security communication protocols such as HTTP or CoAP, TLS or OSCORE. OSCORE profile instantiates the ACE framework for use with CoAP and OSCORE. The OAuth or ACE architecture assumes the presence of three entities: a resource server hosting a given protected resource, a client interested in obtaining a representation of the protected resource hosted by the resource server, authorization server, a trusted third party that issues access tokens needed by the client to access a protected resource on the resource server. Before a client can request a token and obtain a representation of the protected resource, a couple of assumptions need to be met. First, the authorization server and the client share a pre-established OSCORE security context, allowing them to mutually authenticate and to communicate securely. Second, authorization server and the resource server share a cryptographic key. This key is used by the authorization server to encrypt the token when sending it to the client. The fact that the token is encrypted on the application layer allows the client to present this token to the resource server securely, even when the underlying transport session is not encrypted. When a resource server receives, decrypts, and validates that the token indeed comes from the authorization server, it can install a dynamic OSCORE security context with the client. The resource server then allows the access to the protected resource over this OSCORE secure channel. The three roles from the previous slide have been implemented in different projects of the OpenWSN environment. OpenWSN is a project founded at UC Berkeley, now led by INRIA, that implements the 6-dish protocol stack. The ACE framework has therefore been mapped to a 6-dish use case as follows. The authorization server is co-located with a 6-dish entity called Joint Registrar Coordinator, or JRC, that is in charge of managing the network join process. The role of the ACE authorization server has therefore been implemented within the OpenWSN software project in Python. The resource server is co-located with a constrained 6-dish node. The role of a resource server has therefore been implemented within the OpenWSN firmware project in embedded C. Finally, the role of a client has been implemented as a generic CoAP application that can run anywhere on the internet. The code of the ACE client is contributed to the OpenWSN CoAP project and is written in Python. I will now proceed to the demonstration where I will show the access of a protected resource hosted on a 6-dish node. To demonstrate the access of a protected resource, I will launch OpenWSN in simulation environment and monitor the packets exchange with Wireshark. I will first compile the firmware of the OpenWSN project where resource server is hosted. In the firmware code, the resource server exposes a resource with a URI path resource1. Then I will launch the OpenWSN in simulation mode and create a simulated network of 2 nodes. Apart from creating a simulated network, this command also starts the execution of the software part of the OpenWSN project, where the role of the JRC and the authorization server is implemented. When the network is created, I will set the first node to act as the border router. This will trigger the second node to join the network and start acting as a resource server. In the same time, I will start the packet capture in Wireshark on the TAN interface where the simulated packets are exchanged. The client is a generic application that can run anywhere on the internet. In our case, client will run locally on my machine, and the client first tries to access the protected resource over unprotected transport. As we can see from the log, the client received the 401 unauthorized error containing the authorization server information that encodes the IPv6 address of the authorization server as well as the full URI, absolute URI. We can also see this in Wireshark, where we see the request and the unauthorized response. The client application prompts us whether we want to go ahead and request the access token from the authorization server. I will respond with yes. The client then requests the access token from the authorization server, which we can see in Wireshark. This exchange happens over OSCORE, and from OSCORE and the secure channel between the client and the authorization server. In the payload of this response is an access token that is also encrypted by the key shared between the resource server and the authorization server. The client application then prompts us whether we want to send this access token to the resource server. I will respond yes, and we can see new packets being captured in Wireshark here, where the resource server responded with 201 created response, indicating that it was able to successfully validate the access token. The client application then prompts whether we want to access the protected resource over this newly created OSCORE security channel. I will select yes, and in response we obtain an ASCII graphics indicating spots. If we take a look at Wireshark, we can see that this exchange happened over the OSCORE security channel that was just established. Thank you for following this demo. Please check out the other demonstrations that were provided as part of the SPOTS project.